Okay, we start with the fact of y equilibrium, which means we list the forces in the y direction and set their sum equal to 0, because that's what it means to be in equilibrium. Forces add up to 0. Okay, well, in the y direction we have the y component of the gravitational force, that's this purple vector, plus the applied force, the y component of the applied force, times j. Okay, and these are times j. I'm using the j in here. It isn't absolutely necessary to do that, but it really helps focus you on the vector nature of what you're doing, okay? So I kind of recommend it. I don't require it. So we have the applied force multiplied by the y component of the applied force times j, plus the normal force times j, where the gravitational force component in this direction will be the weight, mg, times the sine of 300 degrees, this thing. Okay, and of course that gives you the negative 0.87 mg. Then we have the applied force in the y direction. That's going to equal the applied force times the sine of 190 degrees. And that's going to be negative 0.16 times the applied force. Sine of 190 degrees being negative 0.16. Ballpark, I might be off by 100. Might be off by more than that if I wasn't thinking right, but I think I'm probably okay. It's around 1/6 of a radian, so it's going to be around 1/6. Then the normal force multiplied by j, well, we don't know what the normal force is, but when we bring that term down to this equation, we see that, okay, if all this adds up to the 0 vector, then we have negative 0.87 mg. The applied force has a magnitude that's equal to 1/10 of the weight. So that's going to be negative 0.16 times 1/10 of mg. And then you got the normal force, and those all add up to 0, and I don't have vector signs over anything anymore. Because I can factor j out, and if it's equal to 0, then, yeah, well, let's not worry about the details of that. Okay, then I easily solve this for the normal force, and I get, just doing it in my head, I think it's probably closer to 0.89 mg than it is to most other possible multiples of mg, to two significant figures, but I could be off by, 1, 0.01. You work it out, and you can get a couple, you can get at least another significant figure if you wish. Well, so we have the normal force, and this makes sense. If there was no applied force, the normal force would just be equal and opposite the gravitational component in the y direction, which would be 0.7 mg. Okay, the normal force would be 0.7 mg. Since the applied force is pushing down into the incline, well, that gives us a little extra force, and I'm thinking that raises us to 0.88 or 0.89. Okay, don't think it goes much over 0.89. Maybe even it might round off to 0.8, but I think it may be. I'm reasonably confident it rounds off to 0.89. Now, actually thinking about it, I think maybe it rounds off to 0.88. It's going to be one of the two. Again, if I'm thinking right. Okay, the x forces now. What can we say about the x forces? Well, we got them listed here. We're going to have the x component of the gravitational force times I, the frictional force times I, and the x component of the applied force times I. The gravitational component's mg cosine 300 degrees. And that's going to be 0.5 mg. Cosine 300 degrees is 0.5. Frictional force is 0.3 times the normal force. Okay, that was just given. And the applied force is at a 190 degree angle, so the x component is the applied force times the cosine of 190 degrees, which is negative 0.98 times 0.1 f normal. Okay, because the applied force has a magnitude of 0.1 times and it's not times the normal force. It's because this isn't friction. Yeah, I wrote that down by similarity with friction because I wasn't thinking. So let me correct that. It was stated that the applied force is 0.1 times the gravitational force. And that's the whole gravitational force. And I had a good wet spot on here. Come on. Where'd you go? I don't know. Okay, that makes this 0.87 mg. And that's actually going to have an influence here, so I'm going to correct that and then explain it. Okay, so that'll be 0.085 with all the rounding and so forth. Okay, so the F grav is 0.87 mg. Negative 0.098 of that is negative 0.085. Now, down here I've factored out the mg because every one of these terms has an mg. So we can see where the negative 0.085 came from. The 0.5 is obvious. And 0.3 times 0.89, I've got 0.24, and that's kind of stupid because 0.3 times 0.9 is 0.27. Okay, so yeah, I'm off by a little bit here. Not sure where I got 0.24. I mean, 0.3 times 0.8 would be 0.24. The 0.3 times 0.9 is closer to 0.27. And it's really pretty close to 0.27. So I'll fix that, and that actually makes this number a little bigger, and this number, and this number, and any other 0.65. Okay? So that's 0.27. So that's going to make this between 0.68 and 0.69. It's going to round off to 6/8, and then all these are going to be 6/8. Okay, so now just correcting the numbers, I get 0.68 mg times I. Okay, well now, what's the acceleration? Well, I add the x acceleration to the y acceleration. And that's going to be x net force divided by mass plus y net force divided by mass. The x net force is this. We got this by adding all the forces in the x direction divided by the mass. And of course, the net y force, since we chose the coordinate system so that, among other things, the net force in the y direction be 0, we'd have y equilibrium, it's going to be just 0. And we can write it as 0j just so we can have an I and a j and we know exactly what we're talking about. But of course we're going to get nothing out of this, and out of this we get 0.68 g. So our acceleration is 0.68 g times I being the unit vector in the x direction, so we know that we have an acceleration. It's about 2/3, a little more than 2/3 the acceleration of gravity in the direction down the incline. And yeah, and that makes perfect sense. It doesn't make sense if you think about it the way I just did for an instant. If the object was coasting down the incline with no friction, then it would have an acceleration just 0.5 mg. Okay, neither of these other forces would be there. So why does it have a greater acceleration? That's a little counterintuitive. Well, the reason is we're going uphill. So friction is acting downhill. So friction's resisting our motion. That gives us a greater acceleration down the incline because we're moving up the incline. Down the incline is a direction that resists motion. Okay? If there was no friction, even if we were moving upward and no applied force, no friction, no applied force, even if we were moving upward, we'd have an acceleration of 0.68 g down the incline. So we have an acceleration in this direction that has a greater magnitude. It's greater than it would be Otherwise, because we're moving up, the incline and friction is acting down.